At the end of the last video, I told you that there's one more proof rule that doesn't fit the pattern. So here is an example of a formula that we'd like to be able to prove, P or not P, but it turns out that it's not possible to prove this formula with the proof rules that we have so far. If you think about it, the only possible proof rules that we could apply here are or introduction left or right. And in each case, we either have to prove P or we have to prove not P. And we can't do either of those things. So in both cases, we're stuck. It makes sense that a proposition is either true or it's false. So really, this formula is encoding the fact that our logic has exactly two truth values, namely true and false. It's maybe surprising, but it turns out to be really useful to have the option to drop this assumption that we have exactly two truth values. So it's quite useful that we're going to have a specific proof rule that encodes that fact, because later on we're going to sometimes switch off that proof rule. So a simple example of why you might want to do that already comes up in digital circuits. So true and false correspond to things that can physically happen in a wire, but maybe we also want to take seriously the fact that the physical wire can get into an intermediate state that doesn't behave like either true or false. Okay, so our new proof rule is called by contradiction with a capital C, because ask is case sensitive. So if I send prove P by contradiction, then ask says we have to prove false given not P. So the proof rule by contradiction is quite similar to not introduction. So if I say prove not P by not introduction, then ask says we have to prove false given P. If I instead say prove not P by contradiction, then we also have to prove false, but instead of being given P, we're given not P. Okay, so I promised that we'll be able to prove P or not P, so let's see how that proof works. I'm going to start by writing by contradiction. So ask tells us that we have to prove false given not P or not P. So the only thing that we can really do now is to ask what we can do with our hypothesis. So I'm going to say from not P or not P. So ask tells us that we have to prove P or not P. So it looks like we've gone in a circle and got back to where we started. But actually we haven't, because this time we have a given, which we didn't have before. So I'm going to say by or introduction right, which means that I have to prove not P. So how can I prove not P? Well, I can do this by not introduction. So I say by not introduction. And now I have to prove false, but now I'm given P, and it turns out that being given P is crucial. So what we're going to do next is we're going to dig deep into our pile of givens and use this original given, P, not P or not P. And I'm going to say prove false from that. And now we're back to the start yet again for the third time, and we have to prove P or not P. But each time we come back to the start, our list of givens is growing. And this time we have P. So I'm going to say by or introduction left this time. And now we're done. Ask accepts this proof because we have P as a given. I can also fill in the missing line and say where prove P given. So this proof is, it's fair to say this proof is not obvious. This proof is something like a work of art. This proof has been handed down to us from the logicians in the first half of the 20th century, who really figured out the entire concept of formal proof systems. We would not expect you to be able to invent this proof from scratch yourself, but you should spend some time playing around with this proof and really trying to understand how it works. In the next video, I'm going to say a bit more about this proof and give you a more intuitive way to think about it. And I can warn you in advance that at least one of the exercises this week is going to need a proof that has a very, very similar structure to this one.